Hello everybody, and welcome back to the live stream. So, our C interpreter has gotten quite a lot of C features already. Like we can manipulate the basic types, we've got pointers, we've got strings. But crucially, it's still a bit useless since we cannot call any functions from the C standard library. So for example, if we want to print values, we're using this intrinsic that we added to the compiler clf_print, which is then manually implemented as part of the interpreter. It would be great if we were able to just call libc functions directly. So the plan for today is to start working on that. We will probably not be able to actually call puts or anything like that because they involve pointers, which means that we need to translate the addresses, which is non-trivial. But let's start with a very simple function, abort. Right? It takes no arguments, it takes no values, just terminates the program. So if we just define it, I'm actually curious what happens if we attempt to call the functions that isn't defined anywhere. Right, we're getting an error for an undefined declaration of abort, which makes sense since we don't have it. We don't have a definition, so we cannot call it. So let's at the first step, let's add a new type specifier, or rather a decl specifier clauf native, and this indicates that this function is actually defined in native code, and that we want to call it. So let's pass that and go from there. So we have a declaration which has a linkage, and let's make it as part of a linkage. So we've got external and internal and none, and let's also add linkage native, which means this one doesn't have a definition, but that's fine. So then in the compiler, we need a bunch of parsing code. So we've got somewhere right here, we're parsing a bunch of decl specifiers. So let's add this one right here. This is a storage. Is it a storage? Yeah, let's just say it's a storage class specifier. And then we've got, after static, we've got clauf native, which maps to clauf native. And then when we are parsing the decl specifier, we've got this really horrible code that I'm always looking forward to editing. Right here, where we are attempting, that's actually not the one, this one. This one. This horrible code that attempts to merge a bunch of qualifiers and type specifiers and stuff like that. And we want to add clauf native. So clauf native specifier clauf native. It is an error if we are having already a linkage. Yeah, so we cannot have multiple linkage specifiers. And then we just say this has the linkage native, and then we continue. So now there are probably a couple of more switch statements that we need to adjust. Let me see if I can find them. Right here, so we've got linkage internal, linkage native, and we're crashing. Sure. What? Oh, that's probably, yeah, this is probably null. Oh, right, because we're assuming it has a definition somewhere. Why are we assuming that it has a definition? What are we doing? We're in CodeGen, we're assuming it has a definition. Sure, and it doesn't have one, so we're crashing. That makes sense. But I'm curious, like we had the compiler error message about undefined, right here, undefined definition. Why are we not getting that? Right, because we are only handling that for stuff with external. I'm pretty sure that's a bug. Like we're only doing external, collecting external definitions, and then we're resolving them. But if we are doing something like that, right? Invalid declaration specifier for what? Are we just not supporting static functions? Apparently we're not supporting static functions, so that's not actually a bug in that sense. Okay, since we're not supporting them. Okay, let's keep them in mind to do that sometime later. Okay, so now we are parsing, but we're crashing because we don't have a definition for it, which is like to be expected. We just need to implement the logic, implement the logic that calls a native function. For now, let's just say if we're having a function decl whose linkage is native, let's just for testing purposes, let's just push null onto the stack, so we don't have a segword. Okay, right. Instead, we're having a really long what's going on? Stack trace here. Okay, that's odd. Why? So what the hell? Like we apparently having like a really long stack trace. Okay. So somewhere we're doing like panicking stuff. Let's see whether I can debug that one. So we create the program, then we execute it. Do we have like a custom? Okay, we don't have a custom panic handler. So let me just set a breakpoint right here. Right. Oh, we're having a stack overflow. Oh, okay, interesting. So we're pushing null, which just so happens to be the address of the main function itself, which isn't what I was expecting. That's okay. That explains the stack trace. So apparently, this seems like a bug in clauf. Null shouldn't be a valid function address as well. So what's null? Now I sets all bits really, and all bits corresponds to main function. That's really odd. Right, so we've got like the function enter. So what we are actually pushing like here is we are so this evaluates to like a special instruction. That's odd. That's really odd. So I just want to crash the bytecode here at some point. So let me just put Leo instead, just so that Leo also. Okay. You maybe right. I was expecting to get this panic method instead of a stack overflow. So this is what we're having here, but crucially we're parsing it. This is a native function. So let's commit that part. The AST CodeGen compiler parse clauf native storage class specifier. Okay, and then I've got something here that I'm getting back to. Okay, so now the tricky part. The goal is to call a function. Hang on, my phone's ringing. So the goal is to call a native function. I should leave a message. Okay. So we want to call a native function. So what we're doing is we've got the name of the function that we want to call. It's abort. And we've got the signature. So what we need to do is we need to resolve that name to an address. And then call that with the appropriate arguments. Right? So let's add a new function here. Okay, so we want to figure out where do I put it? Yeah, make it a helper function. So we want to figure out, given a name, look for a function, native function of that name. And that is possible. Apparently I don't have DL open on here because this is an ARM-based thing. What? Like, there's this function. Oh, I probably doesn't have it. I just don't have it installed. No? Okay, that's odd. Is that really not part of... I was just assuming... Yeah, it's... Okay. I mean, it is here. Apparently don't have the man page. That's odd. But anyways, so we've got dlsym right here, which, given a name and some handle, get me the address of a function. So let me get the man page again. It's really odd that I don't have it installed. So dlsym, it takes a handle, some dynamically loaded shared object, which in our case is the current executable, and a name, and we want to get its address, right? So, and we're using as handle, we're using RTL default, which just looks in our current executable. So what we need to do is, let's refactor that later. So right here, so find the native address of the function. dlsym RTL default, and the name is given by the name of the thing. Context as summit. Apparently my context symbols module mod right here. No, let me see what's it called. Context. I don't have the. I need another context parameter because I don't have access to the symbols here. Really? Okay. I've got symbols. Oh, I've got symbols as part of the thing, but I don't have symbols. What I'm doing with symbols? Oh, declare function gets it. Okay. So I just need to pass that along to the context, which is great because it means passing in a bunch of like stuff. So const clof as symbol internal symbols. So then let me finally add a constructor. Let's context symbols right here. Let me fix those errors first. Logger symbols. What's the, this is the first, why don't you? Oh, it's already a pointer. Okay. So we want to pass the symbols. Okay. Back to the code. So let's just assert that we're having something, a non-native function. And then we will what correct error handling. So now we've got a pointer to the function. And what we need to do is call that. So they're calling it because currently we don't supporting any arguments is easy. We just need to, so this is the function address. We just need to cast it to the appropriate pointer. Reinterpret cast like to a pointer that takes nothing and returns something of the address, and then call that. And this would call abort. But we don't want to call abort during coding. We want to call it at runtime. So we need to generate lauf code that calls it, that does that for us. So let's just say, this involves defining a new built-in function for lauf. So let's define that right here somewhere. Lauf runtime built-in. It is called call native. It takes no arguments. Hang on, I need to do something. One second. Okay, sorry about that. So it takes no arguments, has the default flags or something. Runtime flag default, built-in default. Says the name call native, and we're not defining anything else. Actually, it has one argument, which is the address of the function. So function address is the top thing. Then we are doing a reinterpret cast of that to the appropriate signature to get the function pointer. And then we're calling that. And then we are continuing on dispatch. Okay. From now not as address as native pointer. As native pointer. Right here. Okay. And then in where we're doing right here. What we're doing instead is we're pushing the address onto the stack. I don't have the correct load version for that. Hang on. I've ended that a while back, but I haven't updated that thing appropriately. Okay, so lauf right here, update you, codegen, call native, where was I? Right here. So I want to push the address as bytes. I need to reload CMake to download the address version before I can actually call that function. Okay. Hang on. I did some breaking changes in lauf that we need to fix first. Okay. Slight detour. Build chunk, it now takes a signature. this one, clauf as undefined native global for our program, like so. Okay. Update clauf to latest version. Okay, now we can continue. Okay, now finally we can push the address of the thing onto the stack. So this just pushes bytes onto the stack. And then we're calling the built-in that we just defined. Call built-in b, and the caller is call native. Oh, right. But this does an indirect call of the thing, which is tricky to do. So this is supposed to leave the function address onto the stack, but we don't have a function address for that thing right here. So we need to, special case, actually need to do that logic when we actually do the call for the function. Right here, decl. So at this point, then we can use that logic, except this doesn't necessarily be a function address. Okay. What is the name of your IDE and why do you use it? Oh, this is NeoBIM, and I use it because I've invested many hours programming it so that it's the way I like it. But okay, so we can't do that here because we don't have a function decl at this point. We're only getting a function decl right here, which is annoying because we don't have anything to actually do a function address. So we're supposed to generate. You know what? Let's be sneaky. So I don't have access to the declaration here, and we can also like don't support. So we need function logic, which means that we need to generate a function that does that for us. So we need to generate. Oh, that is annoying. So let's actually not do that here. Let's do that when we do code gen for functions. Right here, we're doing code gen for clauf declarations. Right here, we're doing declare function. Right here. So if it's not a definition or it's a native one. So then we also need to declare a clauf function. That is done then a trampoline that we can use to call the native one, right? That's a good approach. So for the abort function, we're generating a clauf bytecode function, which is a trampoline that then calls the, well, yes. So if the linkage, if we don't have a definition and the linkage is not native, then we don't do anything. And then right here, if it's a definition, we're generating a function body. Otherwise, clauf linkage native, then we are code gen native trampoline. Right, that's a good approach. So then we need to actually define the function code gen native trampoline. Code gen native trampoline, which starts something like that, and something like that. All right. And then we use that logic right here. and then we can just use it generic. So look up if function decl linkage. So if it's a native function, then we do a lookup of the declaration. Otherwise, we're doing a lookup of the definition. Like so. And then native trampoline. So what we want to do is generate that logic, and then we return it. Okay, so let's see what that will do. So we've got a native function abort that is native but doesn't have a definition, which is fine because it's native. Then we're generating a trampoline function right here, which pushes some address onto the stack, which happens to be the address of abort in the libc. This then invokes our built-in, and as we can see, we are crashing with -6, which happens to be because we're calling abort. Let's see, just for fun, what would happen if we were to call something called foo. Then we would, right, we get an unknown native function because we don't have a function called foo. So let's define one right here. Void foo with printf. Let's see, standard IO puts hello from native code. Okay, it can't find because this isn't part of the thing. Can I respond to comments? Sure. Do you have any other question? Okay, so we cannot call it dlsym doesn't find it because this isn't part of a dynamically shared thing. But we can call abort, as indicated by the fact that when we do, we're crashing. My IDE is Neovim, and like I really use it at this point because it is a sunken cost fallacy. There are like 2,000 lines of Vim script that are powering a bunch of stuff, and it's just great. Works for me. Right, there is no deeper logic at this point. Like I like Vim key bindings, and I could switch probably to like Visual Studio Code or something with Vim mode. But why? Right? I mean, this works for me, so I just keep using it. It's also quite nice because I'm totally not on my like I'm actually SSH on a different machine. Here, not on my computer where I'm streaming this from, so this is nice. Okay, but we can call native functions as long as they don't take any arguments and don't return anything. Support calls for native functions with signature void. Yeah, that's signature. Okay. Now let's make a level up, and we want to call exit. So that is exit, which takes an argument. First issue. Exit, as defined by libc, takes an int, but our int in clauf is 64 bits. So this actually isn't the correct signature. On Linux, int is 32 bits, and in our interpreter, 32 bits corresponds to short. I'm pretty sure. Let's see. Inst return of exit. Oh, I'm messing something up in Cogent. But yeah, I'm pretty sure short is 32 bits. Yes, 32 bits. So when we need to take an int, then we Okay, so that is the signature expressed in our tabs. So what we need to do is to, in the code encode, for a native global, native trampoline at this point. So we are, why are we doing that, I wonder? So here we need to handle arguments. So we've got arguments, right? And we need to store them in memory. Right, this makes sense. Let's copy that. This will make sense later on. So now our function takes all the arguments and stores them in memory. And then we need to pass them on to the built-in that calls our native function. So we need to pass in not only the function, but also the arguments. So let's give you two parameters. Let's go to the button. So this built-in takes two arguments. vstick pointer 0 is the address of the function that we want to call, and vstick pointer 1 is an address to an array of pointers to the actual arguments, right? So we've got the address right here, and then we've got the arguments right here. This is the native address. This is the another one. And then the idea is that we somehow need to cast you to the correct signature. So in this case of exit, it would be that one. And then we are passing in like the first argument from the array, copy that over, put that, and so on. But that's a bit tricky to implement, which is where libffi comes in. So libffi essentially does that for us. I've copied the example right here from the hello world example. So we define like a type given its signature. So we want to like define like this function, which has, in this case, they're calling puts, which has uses the default argument, has one argument of type pointer, returns assigned int. Has one argument of type pointer and returns assigned int, and then we can call it by passing it the function pointer, a pointer to the return value, and the array pointers of arguments, which is exactly the information that we're having right here. So this is essentially what we are doing. So let's also pass in the sif. vstick pointer 2 is the native address of the, what's it called? FFI sif. So we've got the arguments, sif as vstick pointer 2 as native pointer, static cast FFI sif. Okay. And then we just want to do that, essentially. So we want to do an FFI call of the sif using our function address. So FFI call, it takes like a generic one. Function address. We don't have a return value at the one, and we want the arguments. But this expects like a native array, so we need to translate that from a lauf address into a real one. Lauf runtime get if it's a const pointer process bstack pointer 1 as address, and we are bypassing type checking by saying that we just need 1 byte, which isn't 2, but okay. And then we need to cast u to a pointer to void. Okay, so fine, get a new pointer. Okay. You still don't like that? Why not? From FFI. Oh, it's a. Oh, I already have a pointer. So then we will take the address. And then we are popping those 3 arguments and doing the call. Okay. So that's the basic idea. We now get all the function address, the arguments, and like the type. And then we can perform a call. And right here, when we do the native trampoline, we need to create the argument array. Create the argument array. So this is a local. So we're creating a local array. Array layout, the element layout is pointers. And we've got how many arguments, how many parameters we have. So 1 for each parameter. And then we are storing pointers to those parameters. So into the thing. So for auto, let's actually merge those 2 loops. We create variables for all parameters and store them. Right. We then store a pointer to the parameter in the arguments array. So at this point, we've got the argument, so we need to store a pointer to var into the argument array. I don't actually need local variables in this function. Okay. So this means that we need to get the thing auto argument address local. So we get the local address of the argument array, argument address. Then we need the index of the argument, which is the index of the parameter, but the correct one. So that is the index. And then we want to arguments. So we get the base address, we add the index to it. Clauf lib memory pointer. We want to add 2 addresses. Sure, let's panic. And you take the offset, which is the index times the element size. So index int uint index times size of pointer. And then we are storing of type value 0 right here. And what do we store? We store the thing, the address of the local variable. So this code stores the address of the local variable in the appropriate index into the argument array. If I haven't done modulo bugs, I've implemented. Okay. Like so. So then we've got the native function, and then we also need the sif. So let's do that right here. So this involves, we need to get like a pointer, like an array of types. FFI types. They are stored by pointer apparently. And types dot. So here we need to handle the type appropriately. Let's just don't hardcode int. Let's see whether that works first. So I want FFI type sint. I type signed int. Okay. So now we've got the types, and then we can create the sif, which looks something like so. Type void types data right here. Then we're creating a new sif Excel, which then allows us to do the appropriate push. So we need to native address arrays sif. So in reverse order. So here we've got I forgot already. Native array sif. Local address be arguments right here. And let's just see what happens. So we want to call exit1. Okay, we're getting a panic for an invalid address. Okay. So this is our trampoline function. We're creating one parameter, which we're storing as a signed 32 into the variable 1. Yes. Then we're getting the... Oh, so we've gotten off by 1 error right because of right here. So we need to do index 0 is the first one. So index 0, we are storing. So this initializer saves the signed m32 into this variable. Then in this variable, which is our array of pointers, we are storing the address where we just stored the signed 32. Then we are pushing a pointer here, a local address, another pointer, and then we're calling our built-in, and apparently that crashes. So it's probably somewhere inside the built-in that we are crashing. So the function address, this should be the address of exit. And it is. So that part is correct. The arguments and the sif, that part is fine. So that also appears to be like, can I get the ABI? Apparently not. Apparently this is the part that's crashing. Yeah. Yeah, that doesn't appear to be a correct address. So that one's apparently broken. Native trampoline, so what we're doing. Right. So this pushes the, I believe I need you right here. The bytes API isn't particularly type safe. Apparently not, still don't like you. Okay, but that part looks, now we've got correct sif, right? We've got this weird thing with argument types. One argument type, which is an unsigned short. Wait, why are you an unsigned short? Okay, no wonder that we're crashing. The argument is an unsigned short, but it should be, it shouldn't be 1, it should be signed int, which is signed int 32. Okay, let's just see. Okay, yeah, we're crashing somewhere in there. Maybe the argument pointers are... I know what the issue is. So the argument struct contains, what we're storing in the argument struct is the local address of our variable. So the local address of this variable, which contains the argument to our function. But this is a clauf address, not a native pointer. So we need to convert those ones into proper arguments as well. So let's do that. So we are creating a vector of void argument addresses, argument pointers. So, and then we need to iterate over how many arguments we're having. N args. So we start at 0 up to n args. Then we are doing a static cast. So this is an array of pointers. There's an array of values, and we need to convert that into an array of pointers. So pointer get a mutable pointer for argument addresses I dot as address. Again, we are ignoring type checking here, runtime checking, by just saying that we're reading 1 byte, regardless of type, and then we can push you back here, and then we can pass you in. Cannot perform a tail call because we're having a destructor. Right. That's fine. Oh, that's actually not fine. That's an issue. That's going later on. We're still crashing. So let's see. So argument pointers has a size 1, and the first one should be, this should be the pointer that contains our thing. So let's cast you to an int. What? Why are you? But this one works? Okay. Maybe I should switch to a different IDE for the purposes I'd like to get a proper debugging experience here. I'm trying to 1, 2, 3, 4 BF 1 C 0, which is 1. So that part's correct. Like, we've got a pointer to our arguments. We've got the sieve, which has the correct number of types. Oh, the unsigned short isn't the type, it's the type of type. Oh, the type pointer is. Oh, okay. So apparently we are. This vector needs to still live by the point we are doing. So this gets destroyed, but it shouldn't be. So let's also leak you. Like, I'm currently just doing heap memory and leaking it just so it survives long enough. Parameters. I need a separate loop. Parameters. Size. Types. Like so. Okay, something like that. And now the memory should live long enough so that we can actually do the call. sure you're not actually needed because we're currently hard coding. Hey, and now we got exit code 1. And we can also exit with another exit code. Great. That works. So now we can call functions with arguments. Let's make the code a bit nicer. So first of all, we probably shouldn't hard code, should actually generate the actual type here. So let's language of request. Code gen type. Let's rename you to lauf type. Code gen lauf layout. Okay, and let's also do FFI type. Code gen FFI type. So given a type, what's the FFI type? We can copy a bunch of this code. So null pointer. FFI type. Do we have got null? Null pointer is a pointer. FFI type signed int 8. U and 8. We've got separate chars. You do not. Okay, don't need to worry about those. Signed int 16. U int 16. Signed int 32. U int 32. Signed int 64. U int 64. Pointer type. FFI type pointer. So an array cannot actually be passed as a function parameter. Array cannot be passed as function parameter, so we don't need to worry about that. Unreachable function cannot be passed as function parameter, and we also don't need to worry about type qualifier, so we can just recurse. Okay, so now we don't actually need to hard code int. Instead, we can. Apparently we want pointers, which is fine. I can provide you pointers. Are those const? They're not const because this is a C library. Okay, but now I don't need to hardcode int. I can do code gen FFI type param.type. Like so. Oh, right. And then U FFI type. Oh, this is this doesn't return anything. Okay. Okay. Nothing changed, but if we know, we can now mess it up by saying that you take an int. Okay, it still works. Probably because the calling convention is the same, regardless. So maybe not. But we're now generating the correct type. So that's that. So then we've got, like, we need to store the cif somewhere. We don't want to leak it, just leak it in memory, right? That would be bad. And also here in the trampoline, what we need to do right here, where we need to manually dispatch all the things, right? And like we allocate memory to store the actual pointers, and on every call. It would be nice if we only needed to do that once. So let's add some sort of like type to hold all that information and store that as part of something. Let's store it as part of the... Can we just let's like, who owns the lifetime of that? This needs to live as long as the module is alive as well. This gets a module, so we need to like return something that holds a module plus all the FFI functions that we needed to call. So let's define a type for that. Class, let's call it code. Yeah, because code gen returns code, right? So that makes sense. And code holds a module, which is the module that we're executing, as well as all these FFI stuff. So we also got like so let's not overthink it. Let's add like an FFI function, which contains an FFI. I don't know what that actually stands for. Cif. I have no idea. The zip, and then we also need the vector of types. Then a vector of types, argument types, because this has a pointer to that data. So we need to keep that as live as well. And then we've got a vector of FFI functions. Yeah. Which we then... Oh, we can't actually use a vector because we want to take its address. Right, so right here in Kotlin, right here we hard coding the address of the function, which is only not this means that we need to prevent that the address changes while we're adding things. And the neat trick to achieve that is, instead of a vector, use a decl, because decl guarantees address stability of the elements. Decl functions. And let's also store the address here. Let's make you public. Code can be constructed from a module. Let's make it like real public. Okay. Then function add FFI function. Functions dot pushback then. And then this address, because it's a decl, this address never changes. Right here. This is stupid. It's a mess anyway. Okay. This takes ownership over the module. I might now let's add a move constructor to that. functions. What are the functions? Yes, let's make you no accept. We also want move assignment. Functions. It's a neat trick. Like usually, like copy assignment you do with like the copy and swap idiom. We would do like temp other, and then you swap the stuff with temp. However, for move, the moved from state doesn't need to be defined, so you can just swap it directly. So you can save that. And this then means that the moved from object now contains the previous state and is responsible for cleaning it up, which is fine, and it's like a neat trick we can do. Love Adam destroy module. Okay, and then you return code. And then during code gen, you code gen native trampoline also gets like the code that we're building. Pcode. Because what we can then do is move you back to pointer of text. Like so. And then we are creating an FFI sieve. Right here. And then instead of we're also getting like the address of the function right here. And then we are creating like an FFI function code add FFI function, given the sieve, the function address, and the types. You shouldn't store the sieve by thing right here. And this thing now gives us a stable address that we can use right here. So now native address of the FFI function. Static cast FFI function, that type. We stack pointer 0, 1 as native pointer. Right here, and then recalling you function address, the address, and here we need sieve nux, like so. And then here we are creating code. So code of our module, code and native function code, return code. This can fail apparently, which is Really, it can fail? Okay. Right here. So we need to turn you into an optional. No problem. And then I wonder like whether we are okay. Then in the calling code somewhere, right, we've got an unused variable FFI function. FFI function. Right, and then the compilation result is if we don't have mods, then we also return null opt. And this is no longer mod, this is code. Move code. And then let me just adjust you. You don't store the code, you store code. Code. Include 0 code jump. And then finally, somewhere in the main function, right here, result code. Oh, we need an access of a code for the module. Good. So love other module. That code module. Yeah, and then we don't want to do this part. Code value. Okay. Oops. Why are we segfaulting? Oh, I think I know why we're segfaulting. Code then call automatic build call native. This one only takes 2 arguments. That should take care of that problem. No. Oh, that is probably doing like it. We're doing a double free somewhere. Yeah, we're doing a double free because the move constructor should invalidate you. That one probably. Yeah, that one works, and we're still returning 42. Okay, great. Let me see whether we can. So this is the part of the function that calls the code, and this needs to do a bunch of argument conversion stuff. I wonder whether we can, like, instead of doing the conversion, that's fine. That part's fine. Code gen native trampoline. This one is a bit messy. This part of the code, I don't really like that. Let's get FFI function. Let's do something like that. Split you into 2. Something like that. Context 0 code. And then we're returning the CFFI, the function address, and the types. If add FFI function Excel, and then here we do code gen get FFI function context code decl. That's a bit cleaner. Like so. Okay. Let's move you over here where we're actually using it. Okay. So that part's nice. Then we've got the this is a bit of a mess. I wonder, don't I have like array? I do have a helper function, array element, which the layout is other type value, and the signature is pointer index. So the pointer is the arguments, and this is the index. So that's a bit cleaner. Yeah, that curious that this one doesn't get constant follow. But anyways, that's a bit cleaner. I like that. So we are getting the like this creates the local. Oh no, I can't type layout. Yes, that is nice. I like that. Okay. So those are functions with arguments. Let me actually see whether they are like browsing the C standard library. Most functions either take pointers or floats, and we don't have neither. So there isn't really a whole lot of stuff we can do. Oh, we can test IMAX apps. That is a return value. Okay, so let's test that now. Let's commit. We don't need this part anymore. Support native functions with arguments. Okay, so return values. In principle, the same deal. Code gen native trampoline. All we need to do is right here, where we're passing void, we need to code gen FFI type decl type. Do we have, I'm guessing type is the return type? No, that's a function type. Type return type, that one. That should be enough to support arguments. So let's try it out by calling, what's it called? At, which again, it takes and returns an int, which means a 32-bit integer, which are spelled short in our code. Right. And of course, we then also need to call native. My language server crashed again. So our call native built-in also needs to support return values. So this one takes a pointer to the return value. So let's take you another argument. Let's also change the order around. So 0 is the native address, 1 is the array of arguments, vstick pointer 2 is an address to store the return value into. Is that correct? I don't care. So you argument array address is vstick pointer 1 as address, auto return address as vstick pointer 2 as address, which means you take 3 arguments. What you're doing here is you're getting the argument array address and casting that into an array. And right here, what you're doing is we're passing the address of the return value, p return address, and we're also just lying about how many bytes we want to access. And now this will write the result of our call into that memory, which we then of course need to populate. So I wonder, like because if we don't have, then we want to pass null pointer, which, hey, nicely translates to null pointer anyway. So that's good. So we've got the function arguments, and then we first push the return value. So if we are having a return value, not, let's do void first. So if you're having void, decl type return type, then we don't need to provide any space. Otherwise, we need to return value, allocate space to store to, inst build local, b auto return type, codegen clauf type, decl type return type. I wonder whether you handle void. You do not. So let's just return null pointer instead. Just so that we can always initialize you. So if you are void, then we're pushing null. Otherwise, we can allocate memory for it. Which we're then pushing onto the stack. Return value. And then after we're calling the built-in, this one is populated, so we just need to load it back. So if this one isn't void, then we just want to load it back. Load field b return type 0. Address b return value before we return. And look at that. Why are we exiting with exit code 5? So we're printing the correct value, 11, which is good. So we're printing 11, but we are something messing up the stack at that part. So this is what our trampoline doing. We are saving the argument. Right, we're saving the argument into a local variable. We're saving the pointer to the argument in the local array. We are pushing addresses onto the stack. We are calling the built-in. We are loading 32 bits out of there and returning, which seems all good. And then right here, we are doing potential integer overflow stuff. We're calling apps. We're calling print, we're popping one value. We're pushing a 0, and we're returning. This all seems correct, so why is the stack? Oh, I'm pretty sure I know why the stack is messed up, because I've messed it up. I call native by forgetting to pop. Yeah. So we can call apps from libc just by declaring it. It will figure it out. It will call it. It will translate the argument appropriately. That's really cool. Let me see whether clean up the code a bit, maybe. So one issue here is that's a separate commit, I think. Captain FFI type. No, native trampoline. Like this one's a bit of a mess. So let's do it like here. Yeah, I mean, that's fine. Probably should. Like, I don't like this stuff right here where we're doing. Yeah, let's do a bit of code duplicate. That is fine. It's not a lot. So if you don't have that, like so, and if it's void, then we don't need to worry with the return value. Okay. That one is fine. Yeah. Okay. I like that part. So now we can call native functions and pass them arguments and get arguments out of them. Support return value in native function. So in the thumbnail for this video, I promised puts, which is tricky because puts takes a pointer and then we need to translate pointers appropriately. So let's not do that today. Let's do that next time. What we can do instead is there's an issue here with our call built-in, call native. That one doesn't do a tail call, which means that every time we call a native function, we're doing like an actual call, which eventually leads to a stack overflow if we're calling like many of them in a loop. And the issue is that we're not doing a tail call is because we're allocating memory right here to translate the argument addresses. So let's instead assert that we are having like less than a fixed number, let's say 256 or something. Too many arguments, like it's probably like overkill. Yeah, let's just make it 32, like that's fine. And use a fixed size array instead. And then we can just say argument pointers I is that. And then since we're not doing, oh, this one's also not great either. Hang on. Dispatch. What's it called? Dispatch something now built in dispatch something. Now dispatch runtime built-in dispatch, that one. So now we can do tail calls again because we're not doing dynamic memory allocation, but we're still doing like adding a bunch of stuff to the stack every time we enter this function, which isn't ideal. So let's just make you global. Since we are single threaded, that's fine. Okay. So this translates the arguments. Then we're doing call, then we're doing the push. Okay. That one should still work. Yep. Ensure tail calls in call native built in. Then the other thing is following situation. Right here. That is an assertion, which isn't nice. So native trampoline. So right here, we are asserting that we are actually having an address. So let's not do that. Let's instead say that at this point, if the function address is null, then we're doing a one-time panic. So we're adding a string literal, build string literal, undefined reference to native function, and then we're just panicking. Global address B message. And then we're just panicking. Undefined reference to native function in foo, right? We could also generate a compiler error because we're actually doing the lookup as part of compile time. But I think like a one-time panic is fine. Like it's sort of like a one-time thing. Like we at one time we're looking for the thing dynamically and then panicking. So let's see. Panic if the native function could not be found. So that is really cool. Like we can just define a whole bunch of functions and just call them seamlessly. And it will just... Apparently not. It will just work, was the sentence I was about to say. Oh. No problem. And it will just work, right? So abs of -11 is 11, and then we are returning with exit code 42 because we're calling exit. Right? We can just call arbitrary function from libc. There are two things that we need to tackle. The first is support for pointers. So I want to call puts, but that one will not work. This will crash, because what we're actually passing here is like a clauf pointer, which is not a native pointer. So we need to do a separate step to translate pointers. This is something that we need to, and also like it's annoying, like exit takes an int, but an int in clauf is 64-bit, not 32 bits. So we need to actually pass short to get the 32-bit int, which is a bit weird. So what I imagine is something like clauf native int, and this will then mean like the actual native one. But those are two features that we will tackle next week. Thanks for everybody who stopped by. Hope you had fun, and until then.